Welcome back. Yesterday we discussed the classification of states into recurrent and transient states or recurrent classes and transient classes, and also into periodic and aperiodic states and periodic and aperiodic classes. Okay. So, today we will discuss the matrix representation and stationary distribution. Before that, I want to make an important definition. A class of states which is both recurrent and aperiodic is called an ergodic class. Ergodic class. A finite state DTMC which consists entirely of one ergodic class is called an ergodic chain. This is just a definition. We know that all states in a class have to be either all recurrent or all transient, right. Similarly, we also know from the previous module that a class, if all states in a class have the same period, right. So, if even one state is aperiodic, the entire class is aperiodic. So, if you have a class that is both recurrent and aperiodic in a finite state Markov chain, such a class is called an ergodic class, all right. And if a finite state DTMC has only one ergodic class, then that chain is called an ergodic chain, all right. See, these ergodic chains are the nicest kind of Markov chains in some sense, in the sense that they have a certain steady state long term behavior, which we will study very soon, all right. So, loosely speaking, ergodicity means that time averages and ensemble averages are equal, and we will see that why these aperiodic recurrent Markov chains are called ergodic. It's essentially because after a long time, these kind of Markov chains converge to a steady state distribution. Okay, we will see that in a little bit. It's an important result, right? But for now, this is just a definition. Ergodic is just a name. All right. There's also another definition, another theorem I want to state, which I probably should have done yesterday in the last module, is that for a finite state, let's say for an ergodic, so if a Markov chain is ergodic, so for an ergodic finite state DTMC, the Pijn, the NStep transition probability, which if you recall is probability that xn is equal to j given x naught equals I. So, this is strictly greater than 0 for all I and j in the state space whenever n is greater than or equal to m minus 1 whole squared plus 1. Okay. So, here this big M is the number of states. So, this is a finite state DTMC, ergodic finite state DTMC, where M is the total number of states. Okay. M is some big M is some finite number. What we are saying is that for n large enough, when n is roughly like m squared, all right, when n is bigger than m minus 1 squared plus 1, then you are guaranteed that the n step transition probability is positive for every I and j, all right. So, there is a positive probability of going from I to j in n step when n is like m square, when the square of the number of states, all right. So, this basically means that in an ergodic chain you can go from any state to any other state after some amount of time, right. There is a positive probability of doing so, all right, and this greater than or equal to can be met with equality for some Markov chains. So, the proof of this I am not going to do. There is a there is a guided proof given in Gallagher exercise 4.5 gives a guided proof for this. May not be worth spending class time on this, but yeah. So, this can be proved, and this equality can this greater than or equal to m minus 1 square plus 1 can be met with equalities for some Markov chains. Okay. So, this is a tight bound, all right. So, to summarize, ergodic chain is a chain that consists of one recurrent and aperiodic class, and for such a ergodic chain you have that Pij n, the NStep transition probability, is strictly positive for large enough n when n is like m squared, all right. Now, let us proceed to discuss the matrix representation. So, we are considering a homogeneous DTMC, let us say finite state homogeneous DTMC. Finite state M state homogeneous DTMC. So, what you are given is that P x n given x n equals j given x n minus 1 equals I is some Pij, all right. So, this is this Pij is the transition probability for going from I to j. Now, you define a matrix big P in which this is an m by m matrix, all right. So, this is a m by m matrix in which the ijth entry is simply Pij, all right. Some of these Pij's could be 0, all right. If there is no directed edge between I and j, you will enter 0 in this matrix. If not, you will enter the value of Pij, all right. So, as I runs through 1 to m and j runs through 1 through m, you will get an m by m matrix with the ijth entry as Pij, the transition probability between I and j. Okay. This is known as the transition probability matrix. Okay. So, this is also an equivalent representation of a finite state DTMC. You can either draw the directed graph as we did the last time, or you can just give the P matrix, the transition probability matrix with the Pij entries. So, given one, you can always recover the other. It is a easy exercise to go from the transition probabilities to the directed graph and vice versa, all right. Now, the behavior of this Markov chain can be understood in terms of some of the properties of this matrix, all right. So, we will look at this matrix very closely. Eventually, we will discuss its spectral properties like eigenvalues, eigenvectors and all that, all right. Now, I want to talk about how to recover the NStep transition probability matrix or NStep transition probabilities from the P matrix. Okay. Now, let us say I am just interested in considering P let us say Pij two-step transition, all right. I want to be able to go from I to j in 2 steps, exactly 2 steps, right. So, can I write this in terms of the entries in the transition probability matrix is the question, right. So, essentially I want to go from I to some other state k, right, and then go to j, all right. Notice that this k itself could be I or j, but the important thing is that after 2 steps I have to be in j, all right. So, as you can see, this is you can just use the theorem of total probability, all right. So, you are just looking at, let us write it this way, x n plus 1 equals j given xn minus 1 equals I, alright. So, this is the definition of Pij2. So, which I can just expand using the theorem of total probability into probability of going from, so xn plus 1 equals j given xn equals k and xn minus 1 equals I times the probability that I go from xn equals k given xn minus 1 equals I, right. So, this is the probability that xn equals k given xn minus 1 equals I, okay. And I sum over all k, let us say in this case it is a finite number of states, k is equal to 1 to m, right. So, this k, that the intermediate state I go to could be any one of the other states, or it could be one of the states I and j themselves. The important thing is that you have to be in j after 2 steps at n plus 1, alright. Now, the nice thing is that I can get rid of this guy, does not matter, right, because of the Markov property. So, this is by the theorem of total probability, these equalities by the law of total probability. By Markovity, I can get rid of this conditioning, the purple cross, which leads to, so this term just becomes p xn plus 1 equals j given xn equals k, right. I can get rid of the second conditioning on xn minus 1. So, bottom line is that this becomes sum over k equals 1 to m p. So, this guy is just p k j, right. So, this is p k j p I k, right, and that is what the 2 step transition probability is, alright. So, Pij2 is just that, alright. So, if you were to look at the 2 step transition probability matrix, what really happens is this equation is just the multiplication of the matrix P with itself, alright. You can just write it out and see, alright. So, what we are saying is that the matrix of Pij2, right, is just the ijth entry of P square, right. So, this is just the, if you look at the matrix P square, this guy on the right hand side of this equation is just the ijth entry of the matrix P square, the matrix P multiplied with itself, alright. So, that is something I am going to write, alright. So, maybe I should write, I should write it like this, sorry, yeah. So, the ijth entry of Pij2, the probability of going from I to j in 2 steps, is the ijth entry of the matrix P square, okay. So, similarly, inductively, we can show that Pijn, which is the probability that I go from I to j in n steps, is simply the, you take the nth power of the matrix P and you take its ijth entry, alright. So, if you want to find out Pijn from the transition probability matrix P, what you have to do is to take the nth power of the matrix and then look for its ijth entry, alright. So, Pijn, so there is a common mistake that people take Pijn to be the nth power of Pij, that is not correct. Pijn is the ijth entry in P power n, alright. So, please keep this in mind, okay. So, this is great, right. So, we can characterize Pijn, the n step transition probabilities, in terms of the 1 step transition probabilities by simply taking the nth power of the matrix and looking for its ijth entry, alright. This is true for all I, j in S, okay. Here we don't need any ergodicity or any such thing. Okay, so this is all for any finite state DTMC. No further assumptions.